January 15, 1925. Marion Steam Shovel Company, Ohio. The engineering specifications scattered across Henry Barnhart's drafting table would have horrified every European heavy machinery expert in the world. American foundry workers, casting steam shovel components using methods that violated everything European precision engineering said was necessary for reliable excavation machinery. Through the smoke and sparks of the Ohio foundry floor, massive iron castings cooled in molds 8 inches thick, more than double European standards. European steam shovels required complete rebuilds every 8 to 10 years, precision-fitted parts, complex valve systems, systematic component replacement schedules. Most carried $45,000 price tags that mining companies could barely justify. The Germans insisted continuous heavy-duty operation inevitably destroyed machinery. British authorities declared thick American castings crude and wasteful. European doctrine demanded frequent maintenance over durability. But Barnhart was building excavators with a philosophy European engineers had never imagined possible. Build it thick enough to fix forever. Simple mechanical systems over complex precision parts. Steel cable and pulleys instead of intricate valve networks. 40% more steel than European models. 60% higher costs. 180 tons versus Europe's 110-ton standard. 8,000 miles from European workshops, the most decisive excavation revolution in industrial history was beginning. Not in precision engineering, not in sophisticated systems, but in the systematic overbuilding that would keep American steam shovels digging. For decades, European experts declared impossible. The foundry floor at Marion Steam Shovel Company stretched across 2 acres of corrugated steel roofing, where January wind whistled through gaps that no amount of expansion had managed to seal. Henry Barnhart stood before the largest casting mold the company had ever attempted, watching molten iron flow like liquid fire into cavities that would form the main housing of machine number 4201. At 53, Barnhart had spent more hours inside steam shovel cabs than any engineer in America, and the scars on his hands told stories of every mechanical failure that had taught him what not to build. The mold before him represented everything European engineering authorities declared impossible. 8 inches of solid cast iron where German design specified 3. Mounting points reinforced with steel plates thick enough to stop rifle bullets. Bearing surfaces machined with tolerances loose enough that a competent mechanic could rebuild them with hand tools in a Minnesota mining camp. Barnhart had calculated every dimension based on a single principle that made his educated competitors shake their heads in dismay. Build it so thick you can fix it forever. James Iteber. Wellington Fairfax III arrived that morning in a Packard limousine that cost more than most Marion workers earned in 3 years. His tailored overcoat and leather briefing case marked him as the kind of investor who preferred boardroom engineering discussions to foundry floor inspections. But the $45,000 price tag on each Marion shovel demanded personal attention. Fairfax represented a consortium of Great Lakes mining operations that needed excavation equipment capable of moving 2 million tons of iron ore annually from the Mesabi Range, and European manufacturers had submitted detailed proposals promising exactly that capability at substantially lower cost. The technical specifications spread across Barnhart's drafting table would have impressed any European engineering committee. Bucyrus Erie offered shovels weighing 110 tons with precision-fitted components, manufactured to tolerances measured in thousandths of inches. Their hydraulic systems featured sophisticated valve networks that could modulate digging force with clockwork precision. Steam boilers burned specific grades of coal at carefully controlled temperatures to maintain optimal pressure ratios. Maintenance schedules called for systematic component replacement every 18 months, performed by factory-trained technicians using specialized tools and calibrated measuring instruments. Barnhart's alternative violated every principle those Europeans had spent decades perfecting. His main boom assembly used steel cable over pulleys 30 inches in diameter, creating mechanical advantage through simple physics rather than complex hydraulics. The boiler burned anything combustible, coal, wood, mining waste, even old railroad ties when nothing else was available. Components were designed with clearances loose enough that thermal expansion would never bind moving parts, even during 40 below Minnesota winters, when European precision mechanisms seized solid. Professor Wilhelm's engineering analysis arrived by telegraph that afternoon, transmitted from the German Institute of Technology, in response to Marion's technical drawings. The message contained 43 specific objections to Barnhart's design philosophy, each supported by decades of European industrial experience. Excessive weight would reduce mobility and increase ground pressure beyond acceptable limits. Loose tolerances would create excessive wear and premature component failure. Simple mechanical systems could never achieve the precision control required for efficient excavation. The telegram concluded with a prediction that would haunt Marion's executives for months. American crude engineering methods would result in catastrophic financial losses within 2 years of operation. Iron Mike Kowalski had operated steam shovels for 20 years across mining sites from Michigan to Minnesota, and his daily logbooks contained more practical engineering knowledge than most university textbooks. He understood that excavation equipment lived or died based on its ability to keep working when everything else failed. European shovels required 3-day maintenance shutdowns every 6 weeks. Replacement parts took 8 weeks to arrive from overseas suppliers. Hydraulic systems leaked expensive fluid that froze solid in winter temperatures. Precision boilers required specific fuel grades that cost twice as much as local coal and often weren't available during transportation strikes. Barnhart's thick steel philosophy promised to eliminate every problem Kowalski had documented in 2 decades of operational experience. The 8-inch main casting could be cracked, welded, remachined, and returned to service using equipment available at any railroad shop. Steel cables wore out predictably and could be replaced by any competent mechanic in 8 hours. The simple boiler design would burn anything combustible, eliminating fuel supply problems that had shut down European machines for weeks at a time. Tommy Brennan learned casting techniques from craftsmen who had worked with company founder George King, men whose hands had shaped the first Marion excavators in the 1880s. At 19, Brennan possessed mechanical intuition that formal engineering education often destroyed, the ability to see structural problems through touch and sound rather than mathematical analysis. He watched molten iron flow into molds designed to create components that would absorb shock loads no European engineer believed possible, understanding that American mining conditions demanded solutions European workshops had never imagined. The first machine number 4201 rolled off Marion's assembly line on a February morning when temperatures dropped to 28 below zero. The completed shovel weighed 180 tons, 70 tons more than comparable European designs. Its massive bulk dominated the factory floor like a mechanical dinosaur, all angles and rivets and cast iron determination. Critics from engineering journals photographed it beside sleek European models, noting how primitive American overbuilding appeared compared to sophisticated European precision. Fairfax signed the purchase order with visible reluctance, influenced more by Mesabi Range mining deadlines than confidence in American engineering philosophy. His $45,000 investment represented a gamble that thick steel and simple mechanics could outperform decades of European expertise. The margin for error was non-existent. If Barnhart's philosophy failed, it would bankrupt not just Marion Steam Shovel Company, but the mining operations that had trusted American innovation over proven European methods. Machine number 4. 1201 would either vindicate everything Barnhart believed about durability engineering or prove that American industrial ambition had finally exceeded American engineering capability. Machine number 4000. 201 arrived at the Mesabi Range on a flatbed railroad car that required reinforcement to support its 180-ton weight. Iron Mike Kowalski supervised the unloading process, watching 20 men guide the massive excavator down specially constructed ramps, while steam locomotives provided counterweight to prevent the rail car from tipping. The shovel's 8-inch thick main casting caught morning sunlight like polished armor, and even veteran miners stopped their work to witness what many considered either American engineering triumph or spectacular folly. Kowalski's first operational report, filed March 15, 1927, documented performance numbers that would reshape heavy equipment expectations across American mining. Machine 4000. 201 excavated 2,400 tons of iron ore during its first 12-hour shift, 400 tons more than the European Bucyrus model operating 50 yards away. The Marion's boom assembly lifted 4-ton buckets with mechanical advantage ratios that European precision hydraulics couldn't match, while its simple cable and pulley system absorbed shock loads that would have shattered sophisticated valve networks. The engineering triumph became apparent in details European designers had never considered critical. Barnhart's 2-inch steel cables stretched over pulleys 30 inches in diameter, creating leverage ratios of 4-to-1 where European designs achieved only 2-to-1. The massive pulleys distributed stress across cable surfaces large enough to prevent the concentrated wear that destroyed smaller European systems. When cables did require replacement after 18 months of continuous operation, the process took 8 hours and cost $47 versus 3-day European overhauls costing $320. Henry Barnhart received daily telegrams from mining operations across the Great Lakes region, each containing operational data that vindicated his thick steel philosophy while embarrassing European engineering authorities. The Marion shovels consistently outperformed European models in categories that precision engineering was supposed to dominate. Excavation rates exceeded specifications by 20 to 30%. Fuel consumption ran 15% below European standards, despite the Marion's greater weight. Most significantly, unscheduled downtime averaged only 4 hours per month compared to European rates of 18 hours monthly. The thick main casting proved its worth during a May incident that would have destroyed any European machine. A dynamite blast misfired during ore preparation, sending a 1,200-pound boulder directly into machine 4002, 101's operator cab. The impact cracked 2 side windows and dented the casting surface, but Kowalski continued operation without interruption. European precision castings would have shattered completely, requiring factory replacement at costs exceeding half the machine's purchase price. Tommy Brennan's detailed maintenance logs revealed why American overbuilding succeeded where European precision failed. The 8-inch casting absorbed vibrations that transmitted destructively through thinner European structures. Mounting bolts loosened gradually rather than shearing suddenly. Bearing surfaces wore evenly across large contact areas instead of concentrating stress at precision-fitted points. Every component was designed to fail gracefully rather than catastrophically, allowing repairs using standard tools rather than specialized factory equipment. Professor Wilhelm's second engineering analysis, published in German Technical Review that summer, attempted to explain Marion's success through mathematical models that European theory couldn't accommodate. The thick steel approach violated fundamental assumptions about weight-to-strength ratios, material efficiency, and precision tolerances. Wilhelm's calculations suggested that Marion machines should consume 40% more fuel, achieve 30% lower excavation rates, and require significantly more maintenance than observed operational data indicated. The disconnect between European theory and American results forced Wilhelm to question whether Marion was accurately reporting performance numbers. James Fairfax's quarterly financial reports told a different story entirely. Machine 4000. 201 generated revenue of $12,000 monthly, while European competitors averaged $8,700. Operating costs ran 63 cents per ton, excavated versus European rates of 91 cents per ton. The Marion's ability to work continuously through equipment failures that shut down precision machines translated directly into profit margins that European manufacturers couldn't match. The breakthrough moment came during August, when a bearing failure would have sidelined any European shovel for weeks. Machine 4201's main drive bearing developed excessive wear after 16 months of continuous operation, creating mechanical noise audible 50 yards away. European protocol demanded immediate shutdown and factory replacement of precision-fitted components. Kowalski instead machined replacement bushings using portable equipment, rebuilt the bearing assembly in place, and returned the machine to service within 36 hours at a cost of $84. Orders flooded Marion's factory from mining companies that had witnessed thick steel performance firsthand. Kowalski's operational logs circulated through mining trade publications, documenting specific incidents where European precision failed while American overbuilding succeeded. Mining executives calculated that Marion shovels generated 23% higher annual revenue despite their 60% higher purchase price, creating return on investment ratios that made European alternatives financially irresponsible. The Cyrus Erie's response came in September with announcements of redesigned excavators incorporating American durability standards. Their new models featured casting thickness increased from 3 inches to 5 inches, simplified mechanical systems, and loose tolerances that prioritized repairability over precision. European manufacturers found themselves forced to abandon decades of engineering doctrine to compete with thick steel philosophy they had dismissed as crude American overbuilding. The momentum became unstoppable when Machine 4201 completed its first full year of operation, having excavated 876,000 tons of iron ore, 37% more than European specifications promised. Maintenance costs totaled $4,200 versus European projections of $7,800 annually. The machine had proven that American engineering philosophy could outperform European expertise through systematic overbuilding rather than sophisticated precision. Barnhart's vindication was complete, but the real test lay ahead. European engineers still insisted that continuous heavy-duty operation would eventually destroy even the thickest American machinery. They predicted catastrophic failures within 3 to 5 years that would prove precision engineering ultimately superior to crude overbuilding. Machine 4201 would either confirm or demolish those predictions through decades of brutal operational testing that no laboratory could simulate. The fuel crisis struck in November 1932 when railroad workers across the Great Lakes region launched a coordinated strike that shut down coal deliveries for 6 weeks. European steam shovels at mining operations throughout Michigan and Minnesota sat idle within days, their precision boilers designed to burn specific grades of anthracite coal that suddenly became unavailable at any price. Mining executives watched helplessly as excavation schedules collapsed and ore shipments ground to a halt, while European engineering consultants insisted that alternative fuels would damage sophisticated boiler systems beyond repair. Iron Mike Kowalski received different instructions from Marion's engineering department. Henry Barnhart's original boiler design specifications included combustion chambers dimensioned to burn anything that would ignite: coal, wood, oil, mining waste, even old railroad ties when nothing else was available. The thick-walled firebox could withstand temperature variations that would crack precision European boilers, while oversized ash grates allowed complete combustion of irregular fuel materials. Kowalski began feeding Machine 4201 with a mixture of scrap lumber, waste oil, and low-grade lignite coal that European operators wouldn't have considered suitable for heating buildings. The operational results astonished mining industry observers who had accepted European limitations as engineering fact. Machine 4201 maintained full excavation capacity burning fuel combinations that European shovels couldn't tolerate. Steam pressure remained constant despite irregular fuel quality. Boiler efficiency actually improved when burning hot combusting waste oil mixed with slower burning wood, creating sustained heat that European precision systems couldn't replicate. While European machines sat cold and silent, the Marion excavator continued moving 2,400 tons of ore daily using fuel that cost 60% less than premium anthracite coal. Tommy Brennan's maintenance reports documented the engineering advantages that Barnhart's thick steel philosophy provided during the fuel shortage. European boilers required precise fuel-to-air ratios maintained through complex damper systems that failed when burning irregular materials. The Marion's simple firebox design achieved complete combustion through sheer thermal mass, thick iron walls that retained heat long enough to burn any combustible material completely. Ash removal systems accommodated the irregular residue from mixed fuels without clogging, while European precision grates required daily cleaning when burning anything except specified coal grades. Professor Wilhelm's Emergency Technical Bulletin, distributed to European manufacturers in December, attempted to explain why American crude engineering succeeded where sophisticated systems failed. European boiler efficiency depended on controlled combustion temperatures, precise fuel preparation, and systematic ash removal, all impossible when burning irregular materials. Wilhelm's analysis concluded that American thick steel boilers sacrificed efficiency for operational flexibility, achieving inferior performance under ideal conditions, but maintaining function when ideal conditions became unavailable. The financial implications transformed heavy equipment purchasing decisions across American mining operations. James Fairfax calculated that Machine 4201 generated $47,000 additional revenue during the 6-week fuel shortage, while European competitors generated zero revenue due to complete operational shutdown. The Marion's ability to burn alternative fuels eliminated supply chain vulnerabilities that could paralyze precision equipment, translating directly into profit margins that European manufacturers couldn't match, regardless of their technical sophistication. Mining companies began specifying fuel flexibility as a mandatory requirement in equipment contracts. Operations managers had witnessed firsthand how European precision engineering created operational dependencies that American thick steel philosophy eliminated entirely. The ability to burn whatever fuel was available became more valuable than optimal efficiency. Burning premium materials, particularly in remote mining locations where transportation strikes could isolate operations for months at a time. Bucyrus Erie's response came in January 1933 with redesigned boilers that abandoned European precision standards entirely. Their new models featured thick-walled fireboxes, oversized combustion chambers, and simplified fuel systems designed to burn irregular materials without damage. European manufacturers found themselves forced to adopt American engineering principles they had previously dismissed as inefficient and crude, acknowledging that operational flexibility outweighed theoretical efficiency in real-world mining conditions. The broader implications extended beyond fuel systems to fundamental design philosophy. American manufacturers began emphasizing operational continuity over optimal performance, designing equipment to function adequately under adverse conditions rather than efficiently under ideal conditions. European precision engineering had optimized for laboratory conditions that rarely existed in actual mining operations, while American thick steel philosophy addressed the harsh realities of continuous industrial operation. Machine 4002, 101's operational logs for 1935, documented 6,200 hours of annual operation versus European averages of 4,800 hours. The difference represented pure profit, additional excavation capacity that precision equipment couldn't achieve due to fuel limitations, maintenance requirements, and operational shutdowns. Mining executives calculated that American shovels generated 38% higher annual revenue despite consuming 12% more fuel, creating return on investment ratios that made European alternatives financially unjustifiable. The innovation spread throughout American heavy equipment manufacturing as companies recognized that durability and flexibility provided competitive advantages that precision and efficiency couldn't match. Caterpillar adopted similar thick steel approaches in bulldozer design. International Harvester redesigned truck engines to burn irregular fuels. American manufacturers collectively challenged European industrial supremacy by prioritizing operational continuity over theoretical optimization, fundamentally changing heavy equipment design philosophy for decades to come. European engineering authorities faced a crisis of professional credibility as American thick steel philosophy demonstrated superior results across multiple industries. Decades of precision engineering doctrine had created equipment that performed brilliantly under ideal conditions but failed catastrophically when ideal conditions became unavailable. American overbuilding achieved adequate performance under all conditions, proving more valuable in practical applications than European excellence under limited circumstances. The fuel shortage had revealed a fundamental truth that European engineers had never considered. In brutal industrial applications, the ability to keep working mattered more than the ability to work perfectly. Machine 4201 embodied that philosophy through every thick casting, oversized component, and simplified system. The real test would come when continuous operation over decades revealed whether American durability engineering could sustain performance levels that European precision had never attempted to achieve. The explosion occurred at 6:27 on the morning of January 14, 1938, when temperatures had dropped to 42 degrees below zero and machine number 4201 was beginning its 13th year of continuous operation. Iron Mike Kowalski had arrived early to begin the preheating routine required for cold weather startup, a process that involved gradually warming the boiler system to prevent thermal shock in the massive iron castings. The blast that followed would either vindicate or destroy everything Henry Barnhart had believed about American thick steel engineering philosophy. The cause was immediately apparent to anyone familiar with steam power systems. Overnight temperatures had frozen water lines despite Kowalski's standard cold weather preparations, creating ice blockages that prevented proper circulation when he fired the boiler at 5:30 that morning. Steam pressure built rapidly in the closed system until it exceeded the relief valve capacity, generating forces that no boiler design could contain indefinitely. At 6,000 pounds per square inch, the main steam chamber ruptured along a welded seam, releasing superheated steam and boiler fragments across 50 yards of frozen Minnesota landscape. The damage appeared catastrophic to European engineering standards. The 8-inch main casting bore a 12-inch crack running from the boom mounting point to the operator platform foundation. The boom assembly had twisted 30 degrees from true alignment, its steel framework bent but not broken by the explosive force. The operator cab was completely destroyed, its steel plates peeled back like flower petals by steam pressure that would have killed anyone inside. Shrapnel from the boiler had punctured the fuel tank, hydraulic reservoir, and cooling system, leaving machine 4201 surrounded by pools of frozen oil and antifreeze. James Fairfax arrived from Minneapolis within hours, accompanied by insurance investigators and European engineering consultants who had predicted exactly this type of failure. Their preliminary assessment declared the machine a total constructive loss. Repair costs would exceed replacement value, and the structural damage to the main casting made safe operation impossible even if economic repair were feasible. Professor Wilhelm's emergency telegram from Germany expressed condolences but noted that the explosion vindicated European warnings about the dangers of crude American overbuilding approaches. Marion's stock price plummeted 37% when news of the explosion reached financial markets. Mining industry publications ran detailed analyses suggesting that American thick steel philosophy created catastrophic failure risks that European precision engineering had specifically designed to prevent. Orders for new Marion excavators were canceled immediately as mining executives reconsidered the wisdom of machines that could explode with enough force to destroy buildings. The future of American heavy equipment manufacturing seemed to hang in the balance. European manufacturers seized the moment to reclaim market leadership they had lost to American durability engineering. Bucyrus Erie executives arrived at the explosion site with proposals for immediate replacement equipment featuring European safety systems that prevented steam pressure from reaching dangerous levels. Their precision relief valves, sophisticated pressure monitoring systems, and fail-safe shutdown mechanisms offered protection that American crude engineering apparently couldn't provide. Mining companies began specifying European safety standards in new equipment contracts. Tommy Brennan accompanied Marion's field service crew to the explosion site, carrying portable machine tools and cutting equipment that represented the company's last hope for salvaging both Machine 4201 and its reputation for engineering excellence. The young mechanic had learned casting repair techniques from craftsmen who had worked with Henry Barnhart himself, men who understood that thick iron could be remachined, welded, and rebuilt in ways that precision components could never tolerate. The question was whether 13 years of continuous operation had weakened the main casting beyond the point where field repairs were possible. The inspection revealed why Barnhart's thick steel philosophy had survived an explosion that would have destroyed any European machine completely. The 12-inch crack in the main casting extended only 3 inches deep into iron that was 8 inches thick throughout. The massive structure retained complete load-bearing capacity despite visible damage that looked catastrophic to observers unfamiliar with casting engineering. The twisted boom assembly had absorbed enormous forces without breaking, bending rather than shattering, because Barnhart had designed every component with safety margins that European precision engineering considered wasteful. Marion's field crew began reconstruction work in February, using techniques that European manufacturers insisted were impossible. They cut away damaged sections of the main casting using oxyacetylene torches, then built up the damaged areas with multiple welding passes that restored structural integrity. The boom assembly was heated, straightened, and reinforced with additional steel plates. New boiler components were fabricated on-site using portable equipment, then installed with clearances designed to prevent the thermal stress that had caused the original failure. The most remarkable aspect of the reconstruction was its cost efficiency compared to European replacement alternatives. Total repair expenses reached $8,400 versus $45,000 for a new machine, or $37,000 for comparable European equipment. Insurance investigators documented that the thick steel construction had contained an explosion that would have required complete facility evacuation if it had occurred with European precision equipment, potentially saving dozens of lives and millions of dollars in collateral damage. Iron Mike Kowalski supervised every aspect of the reconstruction process, ensuring that operational improvements were incorporated to prevent future failures. The new boiler featured enhanced circulation systems and redundant pressure relief mechanisms. Waterline insulation was upgraded to prevent freezing in extreme cold weather. Most significantly, the main casting was remachined to tighter tolerances than original specifications, actually improving the machine's structural integrity through the repair process. Machine 4000, 201, returned to service on April 2, 1939, stronger than before and incorporating operational improvements that new construction couldn't have achieved economically. The explosion that European engineers had cited as proof of American engineering inadequacy had instead demonstrated the fundamental advantage of thick steel philosophy, the ability to survive catastrophic failure and return to service better than before. The real test would be whether the rebuilt machine could continue the operational excellence that had made it legendary throughout the mining industry. European confidence in precision engineering superiority had suffered a devastating blow that would reshape heavy equipment design philosophy for generations. The explosion had proven that American machines could literally be blown apart and rebuilt in the field, while European precision equipment would have been scrapped completely under identical circumstances. Machine number 4. 1201 resumed operation on April 2, 1939, with structural improvements that vindicated everything Henry Barnhart had believed about American thick steel engineering philosophy. The remachined main casting bore tolerances tighter than original factory specifications, while the rebuilt boom assembly incorporated reinforcements that increased load capacity by 12%. Iron Mike Kowalski's first operational report documented excavation rates of 2,600 tons daily, 200 tons more than the machine had achieved before the explosion, proving that proper reconstruction could actually enhance performance rather than merely restore it. The financial vindication was immediate and overwhelming. Total repair costs of $8,400 represented 18% of replacement value, while the improved machine generated additional revenue that recovered reconstruction expenses within 4 months. European manufacturers had insisted that catastrophic failure required complete replacement, but Marion's field reconstruction had created a superior machine at a fraction of new equipment cost. Mining industry executives began viewing explosion damage as an opportunity for improvement rather than grounds for insurance claims and equipment replacement. Tommy Brennan's detailed documentation of the reconstruction process became required reading at engineering schools across America. The techniques Marion's crew had used, in-place remachining, structural welding, and component reinforcement, demonstrated capabilities that European precision manufacturing had never developed. Thick iron castings could absorb thermal stress from welding operations that would crack thinner European components. Oversized mounting points provided sufficient material for remachining to tighter tolerances. Simple mechanical systems could be rebuilt using standard tools rather than specialized factory equipment. The long-term operational proof began accumulating through daily performance records that European engineering authorities found impossible to dismiss. Machine 4201 completed 1939 with operational availability of 94%, higher than any European excavator had ever achieved during its first year of service, much less its 15th. Maintenance costs averaged 67 cents per ton excavated versus European industry standards of 93 cents per ton. The rebuilt machine was generating profit margins that new equipment couldn't match, regardless of its theoretical efficiency advantages. James Fairfax's quarterly reports to investors documented return on investment figures that transformed heavy equipment purchasing decisions throughout American industry. The rebuilt Marion excavator generated $53,000 annual profit versus $37,000 for comparable European machines. Most significantly, the Reconstruction had extended machine life indefinitely. European precision equipment required complete replacement after 8 to 10 years, while American thick steel construction could be rebuilt multiple times using field service capabilities that eliminated factory dependency. The breakthrough moment came in 1942 when Machine 4201 underwent its second major reconstruction without interrupting mining operations. A boom cable failure that would have required factory replacement of European precision components was instead resolved through field fabrication of stronger cable mounting systems. The reconstruction incorporated wartime steel alloys that were superior to original 1925 materials, actually improving machine performance through the repair process. Total downtime was 36 hours versus the 3-month European factory replacement schedule. European manufacturers faced a crisis of engineering credibility as American thick steel philosophy demonstrated sustained superiority across every operational metric. Professor Wilhelm's final technical analysis, published in 1943, acknowledged that European precision engineering had optimized for theoretical efficiency, while American overbuilding had optimized for practical durability. The fundamental difference was philosophical. Europeans built machines to work perfectly under ideal conditions, while Americans built machines to keep working under any conditions. The wartime production boom of the 1940s provided the ultimate test of American durability engineering philosophy. Machine 4201 operated continuously through labor shortages that eliminated systematic maintenance schedules, material shortages that forced improvised repairs, and production pressures that demanded 20-hour daily operation. European precision equipment failed catastrophically under wartime stresses that American thick steel construction absorbed without difficulty. Mining productivity records established during the war years proved that American engineering philosophy had achieved something European authorities had declared impossible: indefinite operational life through systematic reconstruction. Machine 4201 completed its 20th year of service in 1945, having excavated over 15 million tons of iron ore, with maintenance costs that remained below new equipment financing charges. The machine had literally paid for itself 27 times over, while European competitors would have required 3 complete replacements. The post-war industrial boom of the 1950s demonstrated the long-term economic advantages of American durability engineering. Machine 4201 underwent its third major reconstruction in 1952, incorporating hydraulic assist systems and improved metallurgy that extended its capabilities beyond original design specifications. The 27-year-old excavator outperformed brand-new European equipment while operating with maintenance costs 60% below industry averages. Iron Mike Kowalski retired in 1958 after 33 years of operating Machine 4201, but not before training his replacement in the operational techniques that had sustained legendary performance for 3 decades. His final logbook entries documented cumulative statistics that redefined heavy equipment expectations: 250,000 operational hours, 23 million tons of ore excavated, and maintenance costs averaging 59 cents per ton over the machine's entire service life. The ultimate vindication came in 1968 when Machine 4201 completed its 43rd year of continuous operation, having outlived every European competitor by decades while maintaining excavation capacity that exceeded modern equipment specifications. The machine had undergone 4 complete reconstructions, 17 boiler overhauls, and countless component replacements, all performed using field service capabilities that kept it productive, while European precision equipment would have been scrapped and replaced multiple times. The legacy of Henry Barnhart's thick steel engineering philosophy extended far beyond a single excavator's operational record. American heavy equipment manufacturers had built industries around durability-first design approaches that prioritized field serviceability over factory precision. Caterpillar, John Deere, and International Harvester had adopted similar philosophies that made American equipment legendary for operational continuity under conditions that destroyed European precision machinery. The old engineers had understood something that modern sophistication had forgotten. Complexity was the enemy of durability, and machines built to last forever were more valuable than machines built to work perfectly,